Hello everyone. Uh, it's let us to welcome you all to today's week 8 live session for Thermodynamics course. And let me share my screen first. Yes, and yeah. So yeah, hello, welcome you all. I am Thananka Sutia, and I'm basically a PhD student at the Center for Atmospheric and Oceanic Sciences at IISc Bangalore. And in the previous all classes, we have been doing sums related to Carnot cycle. We were doing a little bit of the Rankine cycle, but today we will do a deep of the Rankine cycle and the different types of gas-powered cycles. So we'll wait for one more minute and then probably we'll start today's class. Okay, so let us start. Uh, Steam is generated at a power plant at 8 megapascal and 500 degrees Celsius and is fed to a turbine. Exhaust from the turbine enters a condenser at 16 kilopascal where it is condensed to a saturated liquid, which is then pumped to the boiler. Assuming reversible adiabatic turbine operating under these conditions, you have to calculate the heat transferred to the boiler, the heat released from the condenser, work done by the turbine, and the thermal efficiency of the turbine. Okay, so before going to solve this, let us quickly look at what is basically the schematic diagram of a steam power plant. Okay, steam power plant. Okay, so how does it look? So what happens that there is a boiler at which the steams are generated. The boiler is nothing but this is basically a heat exchanger. Okay, so there is a boiler at which your steam gets generated. That means here the liquid water will be fed and this will undergo this inside the boiler. It will undergo basically, let me change the color. Yeah, so what happens, it comes here, then it goes inside the boiler, and then this whole entire whatever thing is entering here, it gets converted into steam. Okay, now after it gets converted into steam, in the next step what happens, it uh, enters a turbine. Okay, it enters a turbine and undergoes expansion in that turbine. Okay, after that it will meet a condenser where it will release the heat. Okay, and this condenser, it will convert the incoming steam from this turbine. So let us do once again. Yeah, so it enters the turbine and then it leaves the turbine. Okay, in doing so there is some expansion processes going on and there is some work of expansion is released. Okay, then after this what happens, it goes another heat exchanger which we call as condenser. Which we call as condenser. Okay, so and this in this condenser, once again some heat exchanges processes are going on. Okay, this is basically another heat exchanger and it gets converted into liquid state. Why? Because after this it has to enter a pump. Okay, which will push the liquid water from this pressure state, because in this expansion the pressure drop take place. So now again it will pull it back to its original pressure level from where it started, such that this steam formation can take place inside the boiler. Okay, so this is the overall process. Now this is our This is our turbine. Okay, what happens, that steam is generated inside a boiler by somehow, means the steam is generated inside the boiler. We are not at all concerned how is the steam generated, what is the incoming heat energy, how it comes. We are not at all concerned. This will be dealt in great details when you will be studying this heat exchanger courses. So in that case you will be understanding a lot about what these boilers are, what these condensers are, and how this heat addition or heat rejection take place inside those boilers. Okay, now what basically happens is that, once again I'm telling you that okay, there is some amount of heat addition, and due to this amount of heat addition, the steam gets converted. And let us suppose that the state at which the steam is just getting converted is say your state 1. Okay, now after it gets expanded, it is the state 2. Okay, and from when it goes inside the condenser and comes out, it comes out in the state 3, and then it again pumps it to the original pressure level of the boiler. Then this is, we consider this one as state 4. Okay, so the what you call, yeah, so some amount of heat input is done, and due to which the steam is getting converted. Now this steam, it is expanded in the turbine, and in doing so the turbine does some amount of job. Okay, this is work done by the turbine. That means this is the positive amount of work that is done by the turbine. This is the amount of work that is basically necessary for us to say for some application purposes, which we will be using it for other purposes. In some cases what it does, that it is connected to a generator, and then it rotates, and then it produces the electricity. Okay, then after that what will happen, now this turbine now this steam, now since there must be some amount of liquid water, some amount of vapor must be present. So what happens, that this condenser, the heat gets released, Q2 amount of heat gets released, and entire steam at the 2 state, whatever it may be, saturated liquid at the 2 state, is get converted into liquid state, so that the pump, it can push it from pressure P3 to P4, such that it will again start forming steam in this process. And in doing so, the pump will require some amount of work, and that is your call WP. Okay, so if we have to look at in a TS diagram how it looks, so in a TS diagram, okay, so this is one pressure level, okay, and this is another pressure level. Okay, now what it does, that the suppose this is your pressure PA, and this is your pressure PB. Okay, there are two pressure levels, and this is your point 1. Okay, and this is some steam, which is superheated steam, which is generated after it passes from the boiler. So this superheated steam will not now get isentropically expanded. Okay, isentropically expanded, so that's why the S remains the constant. Okay, and then it will reach the state 2. Okay, now after it goes, now this is the 2 to 3 is the condenser process, and what is the final output in the condenser? It is nothing but a liquid. Okay, saturated liquid basically. So this is your state 3. Okay, and after this what happens, the pump again pulls it back to its original pressure level by isentropically compressing it. Okay, this liquid is isentropically compressed by the pump to the state 4. Okay, now if you are interested what amount of latent heat and what amount of sensible heat, then you can also give a 0.5 here, which is basically inside this boiler only 4 to 5 and 5 to 1. So this is the overall entire process of the entire cycle. Now in our case, our pressure PA is given to us. Okay, that is 8 megapascal, and our pressure PB is given to us as 16 kilopascal, which we can write it as 0.016 megapascal, because we already know that whatever steam table I am using, it is basically all the pressures are written in the megapascal. Okay, and what we know that the steam temperature also we know, and that steam temperature, that is basically T1, is our 500 degrees Celsius. Okay, so you know, I think that this is a constant pressure line, so P1, P5, P4 are all equal to 8 megapascal, and this is also another constant pressure level, so P2 and P3 is basically your 0.016 megapascal. Is this clear now? Okay, so then our main objective is okay, so the main objective is to calculate the enthalpies. Okay, our main objective is basically to calculate the enthalpies, so that we can use it in calculating the heat transfer, the work required, and whatever things. And then finally, so what it will be, our objective is to calculate enthalpies at various points. Okay, so let us first go to the steam table and locate this point 1, and in that state we will see our whatever values are required to us. Okay, so our pressure level is 8 megapascal and 500 degrees Celsius, okay, in the superheated state. Yeah, so we have got to the 8 megapascal and we got the 500 part. Okay, this is our 8 megapascal and 500 degrees Celsius, and there we have got that from steam table okay, what we got, that at 8 megapascal and what thing 500 degrees Celsius, what we got, H is equals to 3399.5 kilojoule per kg, and our S we got it as 6.7266 kilojoule per kg Kelvin. Okay, let me check again. Yeah, 3399 and 6.7266. Now in the next step, and we only need these two values, and why we need the entropy values I will tell you just after some time. Okay, then at PB, that is at 0.016 megapascal, we will take these values. Okay, so just wait for some time. At 0.016, yeah, so this is basically my 0.016. okay, so at 0.016 at 0.016 megapascal, what I got VF is equal to 0.0010471 meter cube per kg. Okay, oh sorry, this is 0016. I am very sorry. 0.016. Yes, so this is 0.016, so 1071. Yes, and yes, so yeah, and then HF is 231.67 kilojoule per kg. Then Hg is 2600.6 kilojoule per kg. Your SF is equal to 0.77201 kilojoule per kg, and your Sg is 7.9846 kilojoule per kg Kelvin, and this will be also kilojoule per kg Kelvin. Okay, let me cross check it. 0.77.9846 and 231.2600.6. okay, fine. So now so that means at the point 1 we know everything. Okay, so because this is basically we have calculated at this pressure level and at this temperature, so therefore my H1 will be what? H at 8 megapascal and 500 degrees Celsius. Okay, which is nothing but 3399.5 kilojoule per kg. Okay, and similarly S1 will be equal to S at 8 megapascal and 500 degrees Celsius. Okay, which is nothing but 6.7266 kilojoule per kg Kelvin. Okay, now why I have done this S, I have taken this as also I although I told that our objective is to calculate the enthalpies at the various points, it is because this from state 1 to state 2 it is isentropic. Okay, 1 to 2 is isentropic process. Okay, so what will happen? Therefore my S2 will be equal to my S1, and that will also be equal to your 6.7266 kilojoule per kg Kelvin. Okay, now we can also calculate S2. How? Because this 2 is in between this point and this point at this pressure level, and whenever it is in such case, suppose my dryness fraction is x2, then what will be my S2 from that formula? It will be nothing but SF at this pressure level PB, that is 0.016 megapascal. Okay, SF at 0.016 megapascal plus x2 times SFG at 0.016 megapascal. Okay, so we already know x2, we'll put it here, 6.7266. we know SF and at 0.016 megapascal, and that is basically a 0.77201. okay, we don't know x2, that is what we require. Why we require x2, you'll know after this. And this will be basically Sg minus Sf, that is 7.9846 minus 0.77201. okay, and from here I will get x2. okay, 6.7266 minus, oh shit, 6.7266 minus 0.77201 by 7.9846 minus 0.77201. So here, from here I have got x2 is equals to 0.82. Okay, this is the dryness fraction at the level 2. So if you got the dryness fraction at the level 2, now you need to calculate enthalpy at the 2. So that means H2 will now be what? HF at 0.016 megapascal plus x2 times HFG at 0.016 megapascal, as simple as that. Okay, so from here I can calculate the H2, HF 231.67, and I already got the x2 0.82, and this will be your 2600.6 minus 231.67, okay, kilojoule per kg. Okay, so from here what you will get, so your H2 is 2174.1926 kilojoule per kg. Okay, so I have got H1, I have got H2. Now one more thing, it is telling us that in the condenser the steam gets condensed into a saturated liquid. That means the final state is your 3. And can anyone say what will be then H3? H3 will be basically my HF at 0.016 megapascal, because the third state is nothing but it is a saturated liquid at this pressure level. Okay, so that means this point 3 is fixed. It will be at this point only, the point of intersection between this pressure line and this dome shaped saturated liquid line. Okay, so that's why that will be nothing but HF at 0.016 megapascal, which is nothing but 231.67 kilojoule per kg. Now how will we calculate H4? Okay, how will we calculate H4? Because in this state this is nothing but a liquid state, and here that thing will not work what x1 x2, because this x1 HF plus x HFG is only for this in between these two regions. So this is purely a liquid state. So what will happen, basically, we know that pump work is equals to what? Minus integration of VdP from P1 to P2. Okay, this is basically your pump work. And if you apply this in here, now since this is a this part is a liquid, so from point 3 to 4 the volume will not change much. That's why we have already extracted the VF value from the steam table, so the volume will be that only. So here your pump work will be basically VF times P. In this case our P 1 is PB and P2 is PA, so PA minus PB. Okay, so this is a pump work, and by putting this negative it has already become this positive. Okay, so this will be your pump work. Okay, now this pump work, then it can also be calculated by what? Means it can also be calculated by H4 minus H3. Okay, so therefore H4 minus H3 is nothing but VF times PA minus PB. So from here you will get H4 is equals to H3 plus VF. What is VF? Basically VF at 0.016 megapascal, or even if you take the VF at the other pressure, it will not vary much, okay, because the liquid specific volume does not change too much with pressures, okay. PA minus PB. Okay, so from here you'll get H3 is nothing but 231.67, that is my H3, plus VF is nothing but 0.0010471, 0.0010471 times P, that is 8 minus 0.016. Remember, this is in megapascal, so I need to convert this into kilopascal because this is in kilojoule per kg, so then this will also be in kilojoule per kg. Okay, so from here I got H4 is 0.471 into 8 minus 0.016 into 1000, okay, plus 231.67. so that is basically 240.03 kilojoule per kg. Now we have got all the enthalpy values. Now you just need to calculate heat transfer to the boiler. What is the heat transfer to the boiler? Heat transfer to the boiler will be enthalpy at 1 minus enthalpy at 4, because this is an enthalpy and this is the gain in enthalpy from the 0.4 to 0.1. okay, so heat transferred, therefore heat transferred to the boiler is equal to what? Is equal to Q1, and that will be nothing but H1 minus H4. okay, and what is my H1? Is 3399.5, 3399.5, and this is I have just calculated 240.03 kilojoule per kg. okay, so that will be equal to 3399.5 minus 240.03, okay, that is 3159.47 kilojoule per kg. okay, so this is your heat transfer to the boiler. The next step is heat release from the condenser, so similarly this will be nothing but H2 minus H3. okay, so heat released from condenser is equal to your H2 minus H3, and the H2 value is 2174.1926 minus H3 is 231.67 kilojoule per kg. okay, so now this will be your 2174.1926 minus 231.67. okay, so this is basically 1942.5226 kilojoule per kg. okay, then work done by the turbine. okay, so next is your work done by turbine. Okay, so this is your Q2, that is equals to your WT, and this will be equal to nothing but, because turbine work is 1 to 2, so it will be H1 minus H2. Okay, so it will be H1 minus H2, and what is your H1? 3399.5, this is H1, and your H2 is 2174.1926. okay, 3399.5 minus 2174.1926. so this is your I'm sorry, this is your 1225.307 kilojoule per kg. Okay, now finally you have to calculate the thermal efficiency. So what is the thermal efficiency? Efficiency is nothing but output by input. Let me put another slide. Okay, so now your efficiency is output divided by input. Okay, and what is your output? Output is network. Okay, and your input is Q1, heat input. What is your network? Your network is WT minus WP, and this is your Q1. Okay, WT minus WP, we can also write this one as Q1 minus Q2 divided by Q1, and this we have done a lot of time. This will be nothing but 1 minus Q2 divided by Q1, and we have already calculated these two values, so this will be nothing but Q2 is 1942.5226, 1942.5226, and your Q1 is 3159.47, 3159.47. so this will give you your efficiency. Okay, so this will be your 0.3852, so basically 38.52%. so this is your efficiency. If you have any doubt, you can ask me now. Clear? Okay, now we have already seen that this efficiency is not much, so there are various steps. So I think you know the theories like reheat something and all, so we will just solve the numerical and you will understand that okay, by doing this we can increase the efficiency. Now the same question one, instead of 500 degrees Celsius, if you superheat the steam to 800 degrees Celsius, then you have to only calculate the thermal efficiencies. Okay, you have to only calculate the thermal efficiency. Clear? So that means now this pressure is the same, but instead of my temperature being 600 degrees Celsius, now my this 1 point temperature is okay, so now my 1 point temperature is 800 degrees Celsius, so my T1 is your 800 degrees Celsius, and rest all values remains the same. So that means what I should look now, I should look at 8 megapascal and my 800 degree Celsius. So at 8 megapascal and 800 degrees Celsius, now we have to look, because this is my 8 megapascal pressure line and this is my 0.016 megapascal pressure line. Okay, so now I have to look at 8 megapascal and 800 degrees Celsius. Okay, yes, got it. This 8 megapascal, this is my 8 megapascal and this is my 800 degrees Celsius. So now I am superheating the steam to a further level. Okay, so at that my at 8 megapascal and 800 degrees Celsius, what are my H values? My H value is 4123.8 kilojoule per kg and my S value is 7.5184 kilojoule per kg, isn't it? And I already know the values at 0.016 megapascal. I already know the values, so I will not check it because I have already the slides and I will not waste my time. Okay, is it clear? Because we have to now look at 8 megapascal and 800 degrees Celsius. Okay, now what are the things that will change? Now my H1 will change. So my H1 will be, let me cross check whether I am putting the correct values or not. 4123.8 and 7.5184, correct. Okay, so my H1 will now be what? It will be H at 8 megapascal and 800 degrees Celsius. Okay, so 8 megapascal, 800 degrees Celsius, so my H value is 4123.8 kilojoule per kg. This is kg Kelvin, sorry. And my S1 is S at 8 megapascal and 800 degrees Celsius. Okay, so that means this will be now 7.5184 kilojoule per kg Kelvin. Okay, so then now that means my S2 will also be changed. Now since S2 is equals to S1, so this will also be equals to my 7.5184 kilojoule per kg Kelvin. Okay, so again S2 is equals to SF at 0.016 megapascal plus X2 SFG at 0.016 megapascal. Now remember, the earlier whatever X2 will get, now this will not be remaining the same because now this is getting shifted. Okay, earlier the point was a little bit this side because the 500 degrees Celsius will be below here. Now it is almost here. So since because of that shifting, now this will change. Okay, so from here 7.5184 is equals to, okay, I have already the SF value, it is 0.77201 plus X2 times 7.9846 minus 0.77201. Okay, from here I got X2 is equals to 7.5184 minus 77201, 7.9846 minus 77201. 0.93. So if you remember previous case, we got x2 as 0.82 and now we got x2 as 0.93. That means your dryness fraction is increased, that means your steam quality is increased. And what happens basically, no, if your steam quality is increased, that means more amount of vapor is there, then your blades are, because this is basically from 1 to 2, it is nothing but it is the turbine process, so your turbine blades that remain safe. Okay, if it is more and more condensed, then the turbine blades degrade quickly. Okay, and it may increase efficiency or not, you will see whenever I will do this sum. Now just the first and foremost practical application is that your turbine life cycle will increase. Okay, because now you have increased this steam quality. Okay, now will H3 be changed? The 3 point, is it changing? No, because H3 is still the same. It is nothing but HF at 0.016 megapascal. Okay, which is nothing but 231.67 kilojoule per kg. Now will my H4 be changed? Because we will do H4 minus H3 and we will do new F and this P and C, these are not changing, isn't it? So my H4 will also remain the same as the previous question. Okay, so my H4 will be nothing but 240.03 kilojoule per kg. Okay, is it clear now? We have got all the H values, only the point changes are 1 and 2. Okay, now you have to calculate the thermal efficiency. Okay, now eta thermal is what? 1 minus Q2 divided by Q1, which we have already defined. Okay, so what is Q2? 1 minus Q2 is nothing but this one. This is your Q2 and this is your Q1. Okay, so Q2 is H2 minus H3 and Q1 is your H1 minus H4. Okay, put all these values. H2 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 H2. Oh, I have not calculated H2 only, sorry for that, because I have got the X2 and from that I can calculate H2 is equals to HF at 0.016 megapascal plus X2 times HFG at 0.016 megapascal, and from here I'll get H2 is 93 into HG 2600.6 minus 231.67 plus 231.67 2434.7749 kilojoule per kg. Okay, so this will be 1 minus H2 minus H3, it's 2434.7749 minus H3 231.67, then H1 4123.8, H1 minus H2, sorry, H1 minus H4 240.03. Okay, so here you have got the efficiency as 0.4327, that is 43.27%. So in earlier case we got the efficiency as 38%, now we got the efficiency as 43.27%. so you got it. Now that means that, what does it mean? This means that suppose Suppose we have a steam turbine that is operating between two pressure levels. Okay, that is operating between two pressure levels, and suppose the initially it was in some temperature and it was undergoing this process. Fine, it was undergoing this process. Now by some means we have not done the heating till there, we have done a superheating process, that is it went to the other way. Okay, and rest all the processes will be same. This will be 3, this will be 4. Okay, so this is what this superheating. So because of superheating, efficiency increased. Fine. Okay, moving on to the next question. Now you have to again compare the efficiency obtained in question number 1. If instead of 8 megapascal the boiler pressure now it is 15 megapascal and the turbine inlet temperature is kept at 500 degrees Celsius. Okay, so initial temperature is the same, but now we have increased the boiler pressure to 15 megapascal. Okay, so now this is instead of 8 megapascal this is 15 megapascal. This is the same 0.016 megapascal. Okay, and this is the state 1. From state 1 to state 2 it went. Okay, from 2 to 3 it is in the liquid state, and then from 3 to 4 it went there. Clear? Once again we have to calculate all the enthalpy values. Okay, so that means from the steam table at 15 megapascal and 500 degrees Celsius. Okay, at 15 megapascal and 500 degrees Celsius we have to look at the steam table. So this is your 8 megapascal, 10, 11, 12, 13, 14, then 15 megapascal, and at 15 megapascal go to the 500 degrees Celsius. This, okay, so at 15 megapascal and 500 degrees Celsius, let me put 2 new slides. What we got, H is equals to what, 3310.8 kilojoule per kg. Okay, and S I got it as 6.3484 kilojoule per kg. Okay, so again this other pressure is the same, so I will not put because I have already these values at 0.016 megapascal. I already have the VF value, that is nothing but 0.0010471 meter cube per kg. I already have HF is 231.67 kilojoule per kg, and I have Hg at 2600.6 kilojoule per kg, and I have SF that is 0.77201 kilojoule per kg Kelvin, and I have Sg that is 7.9846 kilojoule per kg Kelvin. Okay, this one we already have. Now that means at my point 1 it will change. H1 is nothing but H at 500 degrees Celsius and 15 megapascal, which is equals to my 3 310.8 kilojoule per kg. Okay, let me put this aside, these are just like the given values. Then I have S1, I will not write it again and again. S at okay, let me write S at 500 degrees Celsius and 15 megapascal, that is your 6.3484 kilojoule per kg Kelvin. Okay, then similar process, S2 is equals to S1 is equals to your 6.3484 kilojoule per kg Kelvin. S2 is also equals to your SF at 0.016 plus X2 times SFG at SFG at 0.016 megapascal. Okay, so from here you'll get this 6.3484 is equals to 0.77201 plus x2 times 7.9846 minus 0.77201. so from here x2 is now equal to 6.3484 minus 0.77201 divided by 7.9846 minus 0.77201. This is your 0.77. so this is your quality of the steam, and if you remember, this is the lowest of the quality of the steam among all the three parts. Okay, that means the first two part, this is the lowest quality. So then from that I can calculate H2 is nothing but HF at 0.016 megapascal plus X2 times HFG at 0.016 megapascal. Okay, so that will be your 0.77 into 2600.6 minus 231.67 plus 231.67. so then my H2 will be 2055.7461 kilojoule per kg. There will be no change in my H3 because it is the same pressure level. To 31.67 kilojoule per kg. Okay, and then H4 minus H3 is equals to VF at 0.016 times 15 minus 0.016 into 1000. Okay, so from here I got H4 equal to 0.0010471 into 15 minus 0.016 into 1000. so that is your plus 231.67 247.3597 kilojoule per kg. Okay, I've got H1, I've got H2, I've got H3, and I've got H4. Okay, now I need to just calculate the efficiency eta, which is nothing but 1 minus Q2 by Q1, and this will be nothing but 1 minus Q2 is your this is Q1 and this is Q2. Okay, this is the 0.3. so Q2 is H2 minus H3 and Q1 is your H1 minus H4. Okay, put all these values. 1 minus H2 minus H3 is 2055.7461. H2 minus H3, sorry, Q2 by Q1. Q2 is what? Q2 is H2 minus H3, correct? 055.7461 H2 minus H3, 231.67 by H1 is 3310.8 H1 minus H4, 247.3597. okay, so this is your 0.40456, that is 40.45%. so you can see that both cases we got the percentage is greater than what we have got initially. Clear? Fine. If you have any doubt, you can ask me. Okay, let us move. If you have doubt, you can ask. Now consider a steam power plant operating on an ideal reheat Rankine cycle. Steam enters the high pressure turbine at 15 megapascal 600 degrees Celsius and it is condensed in the condenser at 10 kilopascal. If the moisture content in the steam at the exit of the low pressure is not to exceed 10.4%, determine the pressure at which the steam is to be reheated, the thermal efficiency of the cycle. Assume the steam is reheated to the inlet temperature of the high pressure turbine. Okay, so now this is a reheat steam turbine. Okay, so I have forgot to tell that this steam turbine, steam power plant, it works on Rankine cycle. Okay, and this was your ideal Rankine cycle. The second question was when you have superheated this Rankine cycle, and the third question was when you have increased the boiler pressure of this Rankine cycle. Now you will do a reheat Rankine cycle. So why this reheating is done, we will learn it after that, but before that we have to look at the schematic diagram. Okay, suppose this is your boiler. Okay, this is your boiler. Okay, now in this boiler your steam is getting formed. Okay, your steam is getting formed and it enters the turbine. Okay, now it is not directly expanded to your condenser pressure. Okay, what it is then, it is partially expanded to some pressure. Okay, it is partially expanded to some pressure, and then what happens, it is allowed to pass through the boiler once again, and then it is reheated. Okay, and then it is reheated and then it is allowed to enter another turbine. It's allowed to enter another turbine, and in this turbine only now the expansion to condenser pressure takes place. Okay, after that the rest all are the same. Okay, this is the condenser, then there will be a pump, condenser, and then there will be a pump. Okay, which will carry back to the initial boiler pressure. Is it clear? So what it does, it basically expands to a certain pressure level. So this is my turbine 1, and within this turbine 1 there will be some WT1. Oh, let me use another color. Okay, so there will be some heat input Q1, there will be some WT1. Okay, so what we'll be doing, it will be expanding to certain pressure levels, and then it will be reheating back in the boiler, and then once again it will be expanding in the second turbine. Okay, since the pressure at this turbine will be higher than the pressure at this turbine, so this is basically called your high pressure turbine, and this will be called low pressure turbine, because the operating pressure of this turbine is higher than the operating pressure of this turbine. Okay, now let me give the numbers. This as say this as my state 1, this is my state 2, this is my state 3, this is my state 4, this is my state 5, and this is my state 6. How it will look in my TS diagram. So this is my 1 pressure level, this is my boiler pressure level, and this is my condenser pressure level. Okay, so this is my boiler pressure PA suppose, and this is my condenser pressure PB suppose. Okay, earlier case was that from here it was directly expanded, but now what happens that from here it expands partially. Okay, and then once again this thing gets reheated here, then it is expanded. Got it? Okay, let me change the color, then you'll understand. So yes, so what happened earlier, we were doing this, okay, throughout. We are doing this, we are going there, and then we are doing this. Now what we will do, we will basically come to here. Okay, at some pressure level we will reheat it to some say temperature here, and then we'll come back through this part. Okay, and then this will be the same, then this will be the same. Okay, so basically earlier we were going through the green part, now we will do in some intermediate pressure, and then we will again reheat it back, and this reheating, it can be some temperature value, and this reheat temperature is given to us. Is it clear the entire process? Then we will move on to the next question. Okay, why it is done you will understand. Clear? Okay, okay, now let me draw them. Okay, so what it is giving to us, okay, this is my initial pressure level, this is my another pressure level. Okay, and say this is my condenser pressure. Okay, now what it is telling, that if this is my PA, and this is my PB, and this is my PC, what is the question telling us? The question is telling us that my PA is nothing but 15 megapascal and my PB is 10 kilopascal. Okay, so PA is 15 megapascal and PB, that is the condenser pressure, is my 10 kilopascal. That is your 0.01 megapascal. Okay, but we don't know what is the intermediate pressure PC. Okay, so that we have to calculate, I think. Yeah, so we have to find out what is the pressure at which the reheat take place. Okay, we'll find it out. What other things are given? So we are given the temperature at this, so that means we know the point 1. Okay, so at this point 1 we know my T1 is what? My T1 is 600 degrees Celsius. I know my T1 at 600 degrees Celsius. What else I know? I know I got this. Okay, if the moisture content of the steam at the exit of the low pressure turbine, which is my low pressure turbine? This is my low pressure turbine, and that is the point 4. Okay, so what it will go? It will basically go on from point 1 to 2 here. Okay, and then it will undergo some reheat process. Up to what temperature it will be reheated? Assume that the steam is reheated to the inlet high pressure turbine. Okay, so this is my high pressure turbine and this is my inlet temperature, so that means these two temperature values will be basically the same. Okay, so it will be reheated to this point and then it will be further expanded. Okay, so this is my 3 and this is my point 4. Okay, then this is my point 5, then finally it will go to this point. Clear? Okay, yeah, so this is 1 2 3 4 5 6. Okay, fine. So what it is telling us that at the low pressure turbine the exit at the steam head should not exceed 10%. That means what? This means that my x4 is equals to 1 minus 10.4 by 100. Is it clear? What it is telling? It is telling us that the moisture content should not exceed 10.4%. That means vapor percent will be what? 100 minus 10.4. Okay, so that one I am dividing by 100 and doing normalized it by 1. So this will be basically my x4. Okay, so my x4 is 0.896. 0.896. Okay, so this is the quality of the steam at the point 4. Okay, so now we have to determine, and one more thing we know. What is we know? We know that T1 is equals to T3 and that is equals to your 600 degrees Celsius. We know these things. Okay, so that means at the point 1 we will know all the enthalpy values, at the point 3 we will know at the enthalpy. So from steam table, what are the things that we require? At 15 megapascal and 600 degrees Celsius. Okay, at 15 megapascal and 600 degrees Celsius, from steam table we get H is equals to 3583.1 kilojoule per kg. Okay, and we get S is equals to 6.6796 kilojoule per kg Kelvin. Okay, also at 0.01 megapascal, what we get? We get Vf is equals to 0.01027 meter cube per kg. We get Sf is equals to 0.64920 kilojoule per kg Kelvin. We get Sg is equals to 8.14 880 kilojoule per kg Kelvin. We get HF is equals to 191.81 kilojoule per kg, and we get Hg is equals to 2583.9 kilojoule per kg. Okay, so we know S1, that is nothing but S at 15 megapascal and 600 degrees Celsius. Okay, that is your 6.6796 kilojoule per kg Kelvin. Okay, we also know H1, that is nothing but H at 15 megapascal and 600 degrees Celsius, which is equals to 3583 3583.1 kilojoule per kg. So this is my H1. Okay, then S2 will be what? It will be basically equal to S1. Okay, and this is your 6.6796 kilojoule per kg Kelvin. Okay, so how do we calculate then H2? We don't know anything about it. Okay, fine. Can we calculate H4? Yes, because H4 is nothing but HF at 0.01 megapascal plus X4 HFG at 0.01 megapascal. And what we have X4, we have all these values, isn't it? So 0.896 into 2583.9 minus 191.81 plus 191.81. So this will be 2335.1264 kilojoule per kg. Similarly, we can also calculate S4, which is nothing but SF at 0.01 megapascal plus X4 times SFG at 0.01 megapascal. Okay, 0.896 into 8.14880 minus 0.64920 plus 0.64920. So that is equals to your 7.3688 kilojoule per kg Kelvin. Okay, so this is your S4. So that again we know that 3 to 4 is an isentropic process, so that means your S3 is also equals to your S4, and that is also equals to your 7.3688 kilojoule per kg Kelvin. Now at this point 3 we have two values, I mean two not values. At this point 3 we know two parameters, one is the temperature and the other is the entropy. So we have, and also we know that this is a steam. At the superheated steam table we have to go and check all the 600 degrees Celsius, okay, and at which pressure we will get S3 is equals to, and at which pressure we will get this entropy. Okay, so we will check for 600 degrees Celsius at all. So we will basically get it at, so what we will, I will write this step. Okay, what will we do? We will find the pressure level at where S is equals to S3 and T is equals to your T3. Okay, for the superheated steam table. This will give us the reheat pressure. Fine. So this will give us the reheat pressure. So we will go and basically, as I remember, 600 degrees Celsius, 7.022, no, it's, I think it's 4 megapascal, 6.5, yeah, in 4 megapascal and 600 degrees Celsius you can see it is 7.37. okay, and what is our value? It is 7.368, which is almost equals to 7.37. so from here what we get, yeah, so from here what we get, therefore reheat pressure, that is my PC, is equals to 4 megapascal, and this is purely from the steam table. Okay, I have got this from the steam table. Now I got enthalpy at 1. I can calculate enthalpy at 2. How can I calculate enthalpy at 2? Because at 2 now I know two values. One is the pressure level and the other is the entropy. So at that pressure level I choose check the entropy thing. Okay, also I can calculate H3. so H3 will be my nothing but H at 4 megapascal and 600 degrees Celsius. Okay, so that will be what, yeah, I can calculate these all values, but first of all let me check what I need to find out. I have calculated the pressure level up to which it is reheated. Okay, and now I need to find the efficiency. Efficiency is nothing but output by input, and that is nothing but 1 minus Q2 by Q1. And what is my Q2? This is my Q2, this is my Q1. Okay, so for Q2 I need H4 minus H5, and for Q1 I require H1 and H6. So out of this I have calculated my H4. So what will be H5 then? H5 is equals to HF at 0.01 megapascal. So that is basically your HF is basically 191.81 kilojoule per kg. And what is my H6? How will I calculate? H6 minus H5, this will be basically Vf at 0.01 megapascal times 15 minus 0.01 into 10 to the power 3, and from here I get H6 is equals to Vf 0.00101027 into 15 minus 0.01 into 1000 plus 191.81. So that is your 206.9539 kilojoule per kg. So I'll put all these values here. 1 minus H4 minus H5. H4 is 2364 minus H4 minus H5 is your 191.81. okay, so this is your 2143.31264, and H1 minus H6, my H1 is 35883.1 minus H6 is 206.9539. okay, this is 3376.1461. okay, 1 minus 0.31264 by 3376.1461. so this is your 0.3651. so that is 36.51%. okay, so I got the efficiency also. Fine. okay, next, consider a steam power plant that operates on an ideal Rankine cycle and has a net power output of 150 megawatt. Steam enters the turbine at 10 megapascal and 500 degrees Celsius and the condenser at 16 kilopascal. Now steam is extracted from the turbine at 0.5 megapascal to reheat the feed water in an open feed water, and when the water leaves the feed water heater as a saturated liquid. Determine the mass flow rate of the steam through the boiler and the thermal efficiencies of the cycle. okay, so now first of all go to the schematic. so this is my boiler. okay, and then from the boiler it comes to the turbine. okay, and from the turbine one part is extracted to the feed water heater. okay, the rest part goes to the condenser. okay, and from the condenser there is a pump that will put it to its original one, and then there is another pump which will put it. okay, so basically what happens that from the boiler, which is a heat exchanger, it comes to the steam turbine. okay, and within that process only one part of this is extracted and it is allowed to pass through the feed water, because that will be allowed in heating the water before entering the pump. It will heat this water. I will tell you why it is done. Okay, then the rest all, it is getting expanded and it comes to this condenser. Okay, then from this condenser it enters a pump, and this pump, this will put it here. Okay, after that these two liquids get mixed depending on, this is a feed water heater. This feed water heater is nothing but an heat exchanger. Okay, now if this is an open feed water heater, these two liquids will get mixed up, and if it is a closed feed water heater, it will not get mixed up. Okay, the liquids will not get mixed up. And then finally this will come here. Okay, so now this is my boiler, this is my turbine. Okay, so this is my condenser, this is my condenser. Okay, this is my pump 1, this is my pump 2, and this is my feed water heater. Now this can be open or closed. If open, mixing is allowed, and if it is closed, mixing is not allowed. Okay, same as this is state 1. At the state 2, the liquid get extracted, then coming out liquid is the 3, then from 3 to 4 is the condenser process, 4 to 5 pump 1, and then this is 6, and then it is 7. Okay, now if I have to draw this one in a TS diagram, okay, so this is my state 1. Fine. Now from state 1 it goes to the state 2. Okay, and in this way, suppose if m amount of mass was coming here, so some amount of mass is getting extracted here at this state. Okay, so this is my state 2. Okay, so say x amount of mass is getting extracted, then now what are the masses that are coming? This is nothing but m minus x mass is coming here. Okay, so this is my point 3. Now from 3 to 4, now this is the condenser process. The 3 to 4 is the condenser process. Okay, the 3 to 4 is the condenser process. Then from 4 to 5 it is the pump 1. Okay, now these two are getting mixed here. So here what it is coming, m dot minus x dot. Okay, here mass is coming at the feed water, mass conservation. So you can get that feed water heater, these two are coming, m dot minus x dot, this is from the 0.5, and plus this x dot is coming. So whatever is left out, it m6 is nothing but m dot. So you can see here whatever m dot was flowing here, it is again coming in here. So if the mass flow rate were here was m dot, so the mass flow rate here was also m dot, because here x dot amount of mass is coming and here m dot minus x dot mass is coming here. Since this is an open feed water heater, so this two gets mixed and finally it's getting m dot. Okay, so this mass conservation is taking place. Okay, fine. So this is taking place in such a way that this get the final state here is it is nothing but a condensed liquid state. Okay, so this is my state 6. Then from 6 to 1, sorry, then from 6 to 7, this is done by the pump 2 process. then this is the overall reheat cycle. So what happened basically, if this would not have happened, okay, if this would not have happened, the heat put would have been done from 5 to 1. Sorry, if this would not have been happened, this is the boiler pressure. So if reheat would not have been done, only this will be changed, okay, because this will come here, okay, so it would have been going here. Say this would have been the 7 dash, okay, from here to here heat addition would have taken place from 7 dash to 7 1. Now the heat addition is taking place from 7 to 1, okay, and H1 minus H7 is clearly less than H1 minus H7 dash. That means if this one would have been Q1 and this one would have been Q1 dash, so Q1 is less than Q1 dash, okay. And what is our efficiency equation? Our efficiency equation is 1 minus Q2 by Q1, okay. So if Q1 increases, what happens? If Q1 increases, my Q2 by Q1 decreases, yes or no? And if my Q2 by Q1 decreases, the subtraction value is also decreases, yes or no? So in this way my efficiency of this part is also increased. So that is why this reheat is done, regeneration is done, so in order to have this increase in the efficiency. So what we will do now, we will find out all the different points, okay. Is it clear? So what it is giving us, it is telling us that there is a net power output of 150 megawatt, okay. So there is a pump work, net power output, what is my net power output? My net power output is 150 megawatt, 150 megawatt, okay. Then steam enters the turbine at 10 megapascal and 500 degrees Celsius. So I know T1 500 degrees Celsius, okay, and I know that this is nothing but 10 megapascal, okay. Then it is telling us that the condenser pressure is 16 megapascal, that means it is 0.016 megapascal, and the steam is extracted from the turbine at 0.5 megapascal, that means this is your 0.5 megapascal, okay. These three pressure levels I know, fine. Now and so what I know, at 500 degrees Celsius and 10 megapascal, what I know, H is equals to 3375.1 kilojoule per kg, okay, and S is 6.5995 kilojoule per kg Kelvin. Also the other two pressure levels at 0.5 megapascal, I know Vf is equals to 0.00109255 meter cube per kg, okay. Hf is equal to 640 0.09 kilojoule per kg. Hg is equals to 2748.1 kilojoule per kg. Sf is 1.8604 kilojoule per kg Kelvin, and Sg is equals to 6.8207 kilojoule per kg Kelvin. Okay, also I know at 0.016 megapascal Vf is Vf is 0.001047 meter cube per kg. Hf is 231.67 kilojoule per kg. Hg is 2600.6 kilojoule per kg. Sf is equals to 0.77201 kilojoule per kg Kelvin, and Sg is equal to 7.9846 kilojoule per kg Kelvin. Okay, so these are the different values from the steam table what I know. Now then H1 is what? This one, 3375.1 kilojoule per kg, and S1 is my 6.5995 kilojoule per kg Kelvin. Now one thing is sure, although I have drawn it this one, I am not sure whether my this is my this point 2 is in the superheated state or is in the saturated state. Okay, so what I should do here, basically here we don't know that the extracted steam is superheated or saturated. Okay, so first we need to find out this, and then we should go for our diagram. Okay, whether it is correct or not, we'll get to know. Okay, so what we know now, since this is an isentropic process, so S2 will also be equal to S1. So S2 will also be equal to your S1, and that will be equal to your 6.5995 kilojoule per kg Kelvin. Okay, now we just need to check, because at this point at this pressure level we know SF and we know SG. If my S2 lies between SF and SG, then my this figure is correct. If it is greater than SG, it should be in the superheated state. Okay. Now SF is this one and SG is this one. So since my S2, okay, what it is basically, SF at 0.5, this is now, it is less than S2 and it is also less than SG at 0.5 megapascal. That means it lies between these two. So therefore steam is saturated. So that is, this steam is not a superheated steam. Okay, that means whatever we have drawn, it is correct. So then now we can go to calculate for the dryness fraction. Okay, so how will we calculate the dryness fraction? Similarly, S2 is nothing but SF at 0.5 megapascal plus X2 times SFG at 0.5 megapascal. Okay, so from here what we can get X2. Okay, that will be nothing but S2 is 6.5995 minus SF 1.8604 divided by 6.8207 minus 1.8604. This is 0.95. So this is my X2. So from here now I will get H2 is nothing but HF at 0.5 megapascal plus X2 times HFG at 0.5 megapascal. Okay, 2748.1 minus 640.09 plus 640.09. So this is 2642.6995 kilojoule per kg. Okay, so I have got H2, I have got X1, so I have got H1, I have got H2, and then I require H3. Okay, similarly S3 is equals to S1. Okay, and that is equals to your 6.5995 6.5995 kilojoule per kg Kelvin. So also we know S3 is equals to SF at now this pressure level 0.016 megapascal plus X3 times SFG at 0.016 megapascal. Okay, so from here I get X3 is equals to 6.5995 minus 0.77201 by 7.9846 minus 0.77201, 0.81. So therefore your H3 will be equal to HF at 0.016 megapascal plus x3 times HFG at 0.016 megapascal. Okay, 0.81 into 2600.6 minus 231.67 plus 231.67, 2150 point 5033 kilojoule per kg. Okay, so I have got H1, I have got H2. Then now what I need H4. H4 is nothing but HF at 0.016 megapascal. Okay, so what is this? HF at 0.016 megapascal is 231.67 kilojoule per kg. And what is my so H5 minus H4 is equals to VF at 0.016 into 0.5 minus 0.016 into 10 to the power 3, and from here H5 is equals to 0.001047 into 0.5 minus 0.016 into 1000 plus 231.67, so that is 232.176 kilojoule per kg. Okay, and then you'll get H6 is nothing but H6 is equals to HF at 0.5 megapascal, and HF at 0.5 megapascal is 640.09 kilojoule per kg. Okay, then again H7 minus H6 is equals to VF at 0.5 megapascal into 10 minus 0.5 into 1000. Okay, so from here H7 will be what? VF is 0.00109255 0.00109255 into 10 minus 0.5 into 1000 plus 640.09, that is 650.46925 kilojoule per kg. Okay, now we need to find out the mass flow rate of this one. Okay, mass flow rate of the steam toddy boiler. We have got all the enthalpy values. Okay, how will we calculate the mass flow rate? We know that the net power output is given to us. Okay, and what will be the net power output? Okay, so the net power output will be we are given the net power output. So net power output, net power is what? M dot times uh, W turbine minus W pump 1 minus W pump 2. Okay, so that will be the mass flow rate. Now turbine has got two works. Okay, so one is so basically what we will do, that for this initial part of this expansion the mass flow rate is m dot, and for this next part the mass flow rate is m dot minus x dot, isn't it? So the work done by the turbine is can be split into two parts, that is m dot into h1 minus h2. So that will be m dot into h1 minus h2 plus m dot minus x dot into m dot minus x dot into h2 minus h3, h2 minus h3 plus pump in the pump, in this pump P1 it is m dot minus x dot. Okay, so m dot minus x dot into h5 minus h4, m dot minus x dot into h5 minus h4. Okay, so this will be negative, sorry, one more minus. Now in this second pump it will be m dot times m dot times h7 minus h6, and this is equals to your net power. Remember, we know all the values of h1 and h2, we don't know m dot and x dot. So this is your net power 1 and this is your equation number 1. So you have two variables, so, two unknowns, so you need one more equation. One more net power formula is what? Q1 minus Q2. Okay, so then what will be my Q1 minus Q2? That is nothing. For the Q1, my mass flow rate is m dot, yes or no, and here my mass flow rate is m dot minus x dot. Okay, so what can I write here? That m dot times h1 minus h7, h1 minus h7 minus m dot minus x dot h4 minus h3, sorry, h3 minus h4, h3 minus h4 is equals to your net power, and the net power is given, and solving these two you will get the mass flow rate m dot. Fine. After that you just have to calculate the efficiency, and for that efficiency you have to just do eta is equals to 1 minus q2 by q1, and you know what is q2. Q2 is nothing but this one, q1 is nothing but this one, so you'll put this and you'll get this answer. Fine. Okay. So I had a couple of more questions to solve, but for the time permit, we will try to solve this in the next classes. In the next class, okay, I'll start with this gas power cycle sums, and then I will uh, teach the other topics. Okay. If you have any doubt, you can ask. I have 5 more minutes left. Okay, thank you for listening.